Nature is nonlinear. Nature is mechanics. Nature is composite. Nature is structured. In short, nature is the dance of nonlinear mechanics, of composite structures. प्रकृति गैर रैखिक है, प्रकृति यांत्रिकी है, प्रकृति समग्र है, प्रकृति संरचित है. संक्षेप में प्रकृति समग्र संरचनाओं के गैर रैखिक यांत्रिकी का नृत्य है. भूमिमंगलम भूमिमंगलम उदकमंगलम उदकमंगलम अग्निमंगलम अग्निमंगलम वायुमंगलम वायुमंगलम गगनमंगलम गगनमंगलम सूर्यमंगलम सूर्यमंगलम चंद्रमंगलम चंद्रमंगलम जगतमंगलम जगतमंगलम जीवमंगलम जीवमंगलम देहमंगलम देहमंगलम मनोमंगलम मनोमंगलम आत्ममंगलम आत्ममंगलम भूमिमंगलम उदकमंगलम अग्निमंगलम वायुमंगलम गगनमंगलम सूर्यमंगलम चंद्रमंगलम जगतमंगलम जीवमंगलम देहमंगलम मनोमंगलम आत्ममंगलम सर्वमंगलम भवतु 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 सर्वमंगलम भवतु 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 सर्वमंगलम भवतु भवतु भवतु.
I was wondering how it's going as far as the videos are concerned, because they're due on Monday. So that's Monday midnight, which means the day between Monday and Tuesday, the 12 o'clock between that. So I hope you're all progressing well. Akshay had asked a question related to that on Teams, and I had replied. I hope others could see it as well. My reply to Akshay. Anybody else? Okay, so I guess things are clear. Do you have any questions related to the video? Okay, I guess not. Then let's get going with today's class. Okay, so we had just started off on this in the curtailed class that we had on Monday, where we were saying that dimensional reduction is not something new to VAM. It's been around for a century or more, as long as beam theories have been there, plate and shell theories have been there, because they're all dimensionally reduced theories. But dimensional reductions typically done with ad hoc assumptions rather than any systematic manner of approaching dimensional reduction. And also when we talk of dimensional reduction, we are not only talking of spatial reductions like everybody else, which of course will also be the focus of this course, that is going from a three-dimensional reality to two-dimensional or one-dimensional model in a spatial sense. But these dimensional reductions can be in other formats too, depending upon other small parameters that are there. So we're not just talking of dimensions related to space, but dimensions related to the problem as a whole, where non-spatial dimensions might be involved. One could be the temporal dimension, but also dimensions associated with the nature of the problem itself. And I've oft repeated the sandwich example, because it's a classic example where dimensional reduction can be done with respect to the relative dimensions of the structure, that is the face sheet thickness to the overall thickness of the sandwich, as well as the relative properties, that is the core, whether it is honeycomb or foam. Its stiffnesses are typically, or Young's moduli are typically much smaller compared to those of the face sheets, especially in the directions of interest. So that could again be a small parameter. So dimensional reduction with respect to all of these small parameters, or even strain as a small parameter, which we always do, especially in a small strain approximation, which is valid in a materially linear model, where still geometric nonlinearity is included. So in all such situations, the problem simplifies. So wherever there is a simplification, we are going to a reduced order problem. So the original problem is a more complex problem involving many more variables. And since we find that the solutions of interest are not much sensitivity towards some of those variables. They are very sensitive towards certain variables and non-sensitive towards other variables. So let the mathematics decide which are the variables towards which the solutions of our interest are not sensitive or very less sensitive, and then drop off the dependencies on those terms, and then retain only the terms which make a contribution, and therefore you're reducing the complexity of the problem. So any such reduction in the complexity is also a reduction in order in that sense. So it's not just the reduction that we are talking about purely in terms of the spatial dimensions. That said and done, we will focus on spatial dimensional reduction in most of the course, but here and now we will see these glimpses of the other kinds of reductions as well in the order. And another thing with respect to order that is important is a lot of beginners get confused between what is considered to be a lower order and higher order. So typically in this terminology, when we say higher order, we mean a smaller term, which means the lower order terms are the leading order terms and the lowest order terms are the leading order terms. And as they go into higher and higher order terms, we are basically saying that they become smaller and smaller contributors, and therefore many of them can be ignored or left out, at least in the initial stages. So that's essentially what higher order means. And the reason why this terminology has come is because these are small quantities, and therefore it's written in the powers of 10 as exponents, and therefore these are negative exponents, and therefore a higher order essentially means that you're talking of a quantity which is much smaller rather than much larger. So this is one thing we need to clarify. Now, whether it is conventional way of approaching dimensional reduction or the way we approach it, we need to see what is the reason for doing it, and also how they have approached it and how we plan to approach it. So let's start very quickly. This is something that I've gone through in detail for almost 4 or 5 lectures in the previous course, so I will not go in as much detail over here, but it's more of a recap, but more from the point of view of what is essential for our course. So just those salient blocks that we will revisit quickly, so that we'll be in a good shape to understand the details of the derivations as we go forward. So let's see the why and how of the conventional dimensional reduced models. So we have seen this argument in terms of why, first of all, we are using shells and beams so frequently in aerospace engineering, and also in most other vehicular structures, be they on land or water or air or even space for that matter. And we see that they are typically made out of combinations of so-called shells and beams, and we use these terms in a very generalized fashion, as you are aware. And so we will very quickly recap what is the motivation for such structures in engineering, and therefore for us to go for dimensionally reduced models. If there were no shells and beams, we would never even be thinking of dimensionally reduced models in terms of spatial dimensions, because that would not be possible and would not be of any utility either. So this motivation is significant, whether it is a conventional way of doing dimensional reduction or the way we do it. So the important thing there was that we recollect that there are 3 functions which are primary to any vehicular structure. The first one that is there is that as is the case with any structure, primary or secondary, it has to resist certain loads, and if it is a connected structure, then it has to transmit those loads from itself to onto something else. So a load comes onto it through some mechanism, and then it has to be transferred to another structural component in some way. So that is one of the functions. So in the case of the aircraft, for example, it could be the aerodynamic load which is coming onto the skin and needs to be transmitted to, let's say, the stringers. So that's one example of that. The second primary function happens to be to provide a certain shape to the overall structure. And in the case of the wing, it has to be a certain airfoil cross section that is needed, and also in terms of the wing platform, the aerodynamics dictates all that, and therefore we need to provide that aerodynamic shape. Even in non-high performance problems where aesthetics or just the looks becomes very you need to have something that is attractive enough, like your video is going to be. So that aesthetic shape sometimes also requires becomes one of the primary requirements of the structure, especially in structures where factors of safety are very large, like for example in civil engineering structures, where architects typically design buildings sometimes in shapes which may not necessarily have a structural logic to it, but just that it needs to look good or look unique or look very different from the others that are already there. And similarly, in the case of the other vehicles on ships, submarines, etc., the hydrodynamic shape becomes critical, or amphibious aircraft where which can land on the water, river fronts, etc. So you need to have both aerodynamic and hydrodynamic requirements over there. And the third and final primary function, there could be many other secondary functions, and here we're talking of unifunctional structures as opposed to multifunctional structures. So even in unifunctional structures, these primary functions are all there. So the third function that is required is, of course, it has to contain something inside. It could be passengers, it could be their cargo, it could be the military weapons, etc. So whatever it is, it has to contain within them, and that content has to be protected from the environment, the temperatures, the humidity, the airflow, all these things, and therefore this becomes the third important function. And we saw that there's a very lucky combination of these three, because to resist and transmit loads, especially bending and torsional loads, we know that the bending stiffness and torsional stiffness will be maximum if we move the material as far away from the neutral axis or the center of twist, respectively, in these two cases. So for in the case of bending, we have to keep material as far away from the neutral axis as possible, which is the reason why I sections have been so popular in civil engineering as well as in aerospace engineering. And therefore you see that that is the requirement as far as resisting and transmitting loads, especially torsional and bending loads, are concerned. Then if you want to provide a particular aerodynamic shape, again we are talking about the external shape of the vehicle, and therefore essentially we are talking of once again material that needs to be the outlier, or one which is farther away to give the shape. And finally, if it has to contain as much payload as possible inside, and all the other subsystems and systems packaged into it, we want to have the internal volume maximized, which again means that for the third function of protecting the vehicle contents also, we require the material to be as far outside as possible. So usually in design there is contradictory requirements, but luckily in this case all three primary structural functions require us to put the material on the outer surface of the vehicle as far as the structural material is concerned, and therefore it is a lucky combination, because none of these three requirements are in danger just by putting material outside. In fact, all the three are benefited by it. So what this means is that we eventually end up with two main kinds of shell structures for aircraft, or for that matter any land vehicle, especially high performance vehicles like racing cars, and marine vehicles as well, like ships and submarines. So in all these cases you have shell-like structures. So in many cases these are thin shells that we are dealing with, and therefore a dimensional reduction is possible from 3D to 2D. But within the shells itself, again there are two types. One for smaller vehicles which are going at lower speed, and those which are higher speed, either higher speed or larger vehicles. So you have two types of shell structures that are involved, which we have seen in detail in the previous course, the monocoque and the semi-monocoque constructions. So the unsupported shells are what are known as monocoque, mono meaning single, and coque basically meaning egg-like structure, which is a shell, and therefore we are talking of a shell like that. But it's very clear that this is okay for small aircraft where the loads are small, especially if it is a subsonic, low subsonic aircraft which is flying at fairly low speeds, and therefore the air loads and the engine loads, everything is small on those aircraft, and therefore even with thin shells we can still go unsupported or just the shell alone, and it should be fine. But what happens once the aircraft becomes larger, or the case where the aircraft needs to be a higher performance aircraft traveling at larger speeds? So we know that the lift is proportional to the square of the airspeed. Similarly, the drag is also proportional to the square of that, and to balance that kind of a drag and still have the required accelerations, etc., we need a larger engine providing a larger thrust. So the aerodynamic and propulsive forces are all large, and for a high-speed aircraft, and similarly for a large aircraft as well, it's quite obvious that even in cruise the lift has to balance the weight, and therefore a larger aircraft means larger weight and therefore larger lift. So essentially we are talking of larger air loads. So what happens with such large aircraft is that obviously the cross-sectional size of the wings start becoming larger and larger, and once you have larger cross-sectional size of the wing or the fuselage, then you also have larger loads. Some of those loads are distributed loads in the true sense. The others are idealized as concentrated loads, but still they're also actually distributed over smaller regions, as we have seen earlier. But in either case, whether such idealized discrete loads or the distributed loads, both their values are going to go higher for these larger or faster aircraft. So then what that means is that the bending stresses are going to be larger, the compressive stress is going to be larger, the torsional stresses are going to be larger, depending upon the kind of loads that that particular structural component is going to resist or transmit. So that means that to be able to do that without failure, that is either material failure or buckling in the case of compressive loads or a few other kinds of loads, we see that we would have the requirement of the shell thickness being larger, because with thin shells we can no longer support that large load which is coming, either because of the large aircraft or because of the faster aircraft. So once the shell thickness goes up, the shell weight and therefore the overall structural weight goes up, and structural weight as a fraction of the overall aircraft weight goes up, which is not acceptable, because there's a certain maximum limit that we are allowed as structural engineers in terms of the material that we can use, and therefore with larger shell thickness and the same material we are going for heavier structure. Even with the use of composites, it's still not possible to sustain that kind of large fast aircraft with just a shell alone. So which means that the shell no longer can be monocoque. You need to bring in something to support the shell, which is what we call as the supporting members, like the stiffeners, which could be stringers, the spars, and also in the transverse direction the ribs in the case of the wing or the tail, and the frames or the bulkheads in the case of the fuselage. So these kinds of beam-like and frame-like structures obviously are one-dimensional structures. We started off with something which is essentially a two-dimensional structure. Which is a two-dimensional structure. So we saw the need to go from 3D to 2D, one level of dimensional reduction. That was good enough as far as monocoque constructions for small, slow-speed aircraft are concerned. But once we are going into more realistic aircraft, which are high-speed and or large in size, then you need semi-monocoque constructions, which means those stiffening members are now one-dimensional kind of members. And frames can always be thought of as combination of beams with certain joint constraints at the location where the where one beam is attached to the other. So that becomes the boundary condition for each one of those beam elements. So essentially, those whether it is frame or beam or an arch, all of those are put together in one paradigm. As we shall see, we put together even shafts and also the columns, etc., all into one of these categories, because essentially what we are saying is one dimension is large compared to the other two cross-sectional dimensions, and therefore we come up with a need for modeling beams as well. It's not just modeling of shells, but modeling of beams as well is essential, and therefore one more level of dimensional reduction, not only from 3D to 2D but also to 1D, is required. So which essentially means that for the same large aircraft or a fast aircraft, if we were to go for a monocoque construction, we saw that the main problem is that the structural weight is too much. But once we bring in the stiffening elements, we can still do with thin shells. Of course, we are adding the weight of these stiffeners, so the beam-like stiffeners, but in spite of that, the sum of these stiffening elements plus the thin shell still is much lighter than the thick shell that would have been required otherwise for a monocoque construction. So the total structural weight comes down, and the concentrated loads also are now not causing any failures in the thick shell at certain specific locations where especially the load is in such a way that the distributed surface area is very, very small, and therefore it's almost like a concentrated load, and therefore the diffusion was not taking place properly in a pure monocoque construction. Therefore now in a semi-monocoque construction, you put stiffeners below the skin at that location where the concentrated loads are there, like for example where the engine is attached to the wing, or the tail or wing are attached to the fuselage, etc. Those locations you would have frames or ribs which can handle such loads and transmit them more smoothly rather than as concentrated or almost concentrated loads. So that diffusion process of transmission is also an additional advantage that you get with semi-monocoque constructions. So now we have seen the motivation for why dimensional reduction is needed, because in real life we are using such kinds of structures, shell and beam-like structures, and therefore there is a need for dimensional reduction. Now this is also something we saw earlier in the previous course. So load-based component classification, whereas in other literature and textbooks and research papers as well, even the one-dimensional entities are classified separately as axial force taking structures. Again, within that there's a further classification depending upon whether they take predominantly tensile loads, in which case we call them as bars, and in the situation where they predominantly take compressive loads, we call them columns. But we combine both of these bars and columns into a single entity which we call as a 1D structure. Not only that, we go on and look at some structures are taking torques only, and therefore in the literature they are classified as shafts. We club them also together into what we call as generalized beams, and we call them also as one-dimensional structures, because one dimension of the geometry dominates over the other two dimensions of the geometry. And finally, one of the most dominant and important loads that these one-dimensional structures need to bear are the bending moments, abbreviated as BM over here, and in which case the literature calls them beams, but we use the term beam to refer to not only the conventional beams but also shafts, columns, bars, and structures which take all of these loads simultaneously. And that is the case in reality, that we see that even though we design it in a particular way, all structures are taking all types of loads in various flight regimes, and therefore we need to, when we talk about a one-dimensional structure, we are essentially talking about something which is able to handle all of these three kinds of loads. That is bending, and again bending can be in two different directions, bending in this direction, bending in this direction, or in any arbitrary direction, which can be thought of as combination of those two in the principal directions. And therefore we are talking of two bendings, the torque and the axial force at the minimum level. In addition, the bending need not be caused by a pure moment. It could be caused by a force distribution, which is what it is in reality in most situations, and therefore you have something called the transverse shear as well. But luckily what happens is there are only 4 degrees of freedom, as can be mathematically rigorously proved, which was done by Berdychevsky almost half a century back, that only 4 of these are independent. The other 2, that is the transverse shear deformation, can always be derived as a function of the especially the bending, but also in a composite complicated geometry you could have couplings from the other things as well. But essentially you don't need to ascribe 2 separate independent variables for that. But where it is necessary to get it out explicitly, we can always do that as an artificial expansion of the problem size, but for all practical purposes it's not at all essential to deal with the transverse shear strains separately. So these are the 3 categories. So the other kind of bending that is there coming from the shear forces is also included in this third, and therefore is included in the so-called 1D structures that we are interested in. And then finally the 2D structures, where the dimensional reduction is simpler, because you're going only one order of reduction from 3D to 2D, and therefore we deal with these as so-called panels, and predominantly they are taking the shear stresses coming not only from shear forces but also sometimes the torsion as well. So torsion or torque that we saw over here not only is taken by the shafts but also to some extent by the panels as well, through the shear stresses that are generated in them. The classic example is of course of the web of a spar, which is essentially like a beam but is also like a plate or a panel, and therefore takes the shear force coming from the lift, but at the same time it also takes the torsion coming from the pitching moment, etc. So in either case they are essentially taking in-plane shear. That is their dominant functionality, and any such situation which could also take the in-plane loads like tension or compression in any of the directions in the plane are all included in that. And as we go to thicker and thicker panels or thicker and thicker shells, the transverse shear becomes important there as well. But just as in the case, just as I described for the one-dimensional structure, those are not independent variables and can always be derived as a function of the other quantities that we have already taken care of. So that's as far as the load-based component classification is concerned. So very clearly from the previous slide as well as the first half of this slide, we have clearly seen the need to model what in reality are all 3D structures. There's no doubt about it. Spatially, they're all 3D structures, just that some dimensions dominate over the other dimension or dimensions, and therefore we take advantage of that situation and therefore come to a reduced order model, which is simpler to handle in lesser complexities, and in terms of a computational implementation they are much more efficient. So that's essentially what is the 1D or the 2D structure. So This means that there's a dimensional reduction of two kinds. One is to these first three categories, axial force, torque, and bending moment in a bar, column, shaft, or beam, in which case we call all of them as a single terminology. So hereafter in the course, whenever we say beams, it need not necessarily refer to the classic beam taking only bending or shear forces alone, but also torques and the axial forces as well, all of which can be occurring simultaneously, and there could be a nonlinear coupling happening between all of them. So even though it could be bending, as the load could be just bending, but it could be undergoing extension as well, it could be undergoing twist as well. So all these get coupled in a highly nonlinear fashion. And also in terms of the cross-sectional geometries, we have arbitrariness in terms of the kind of complexities we can have. The material distributions can be quite complex. We'll see a couple of examples of that. And then also in the one-dimensional direction, in the important direction which is still retained, that direction it need not be straight like this pencil. It could be highly curved, it could be pre-twisted, that is even when there is no load that is acting on it, there is an initial twist that is there for a particular purpose. In the case of the fixed wing aircraft, it's a wash in or wash out aerodynamic requirement. In the case of helicopter rotor blades also, there is a pre-twist that is there in the flex beams in order to make the aerodynamics much more efficient. So in either of those cases, there is a possibility that there is an initial curvature into which we can take the initial twist as also as one of the components into that curvature vector. The first component being the twist, and the other two components being the curvatures in this direction and in this direction, the first direction referring to a pre-twist that is there. So this is one type of dimensional reduction to a beam-like model. The second type is, of course, to a shell-like model. Once again, we are talking about it in a very generalized sense. The shells, what other people might refer to just as a shear panel or as a box beam in which there are shells to take the torsion, etc. All of them we club together as shells, wherever two dimensions are dominating over one of the dimension, which is the thickness dimension. So whether we are doing a dimensional reduction to a beam or to a shell, that is either to 1D or to 2D, in both cases the purpose of doing it is that first of all, such structures exist where certain dimensions dominate over other dimensions, and the reason why we do it for them is that the problem becomes much more efficient to handle. The computational algorithms and the codes become much faster to run on the same systems, and therefore efficiency is increased. So that is a commonality for all dimensionally reduced models, whether it is spatial dimensional reduction or the other kind of heuristic dimensional reductions that I talked about in the case of sandwich constructions and as an example, but many other possibilities are there. In all those situations, the only reason we do it is, first of all, they are there in reality, such kinds of structures, and very utilitarian structures. And the second thing is that not only they make the design efficient, but also they make the computation efficient, and therefore that's why we use it. But there is a price to pay. Whenever we do something in a shortcut, or we do something faster, obviously there is going to be something that we have to pay off, trade off, and that trade off is accuracy. So irrespective of whether we are doing this dimensional reduction by conventional approaches, which is what we are discussing right now, or we are doing it using the variation asymptotic method, always there is going to be an increase in efficiency and a decrease in accuracy. The only thing that advantage that we get in VAM is that the accuracy drop can be controlled, and therefore because we are not making ad hoc assumptions, instead letting the mathematics drop off the terms based on which is to which parameters the energy is not very sensitive, and therefore the accuracy drop might be negligible. So while there is a drop in accuracy, it might be almost almost unnoticeable. You might get, if you plot the stress results that you get out of VAM, stress results you get out of a commercial software like Abacus using 3D finite elements, taking almost 100 to 1000 times more CPU time, you would still see that the stress distribution, if you plot using VAM and using the Abacus 3D finite elements, they will be right on top of each other. It's one curve which will be taking care of both these results, and therefore you're seeing that it's as accurate as the 3D finite elements. But yes, if you go very to the third or fourth decimal places, and then you might see there is some small change, but essentially for all practical purposes or engineering purposes, it's as accurate as the 3D. But you have to remember that in reality these are all 3D structures, but we are modeling it as 2D or 1D, taking advantage of the problem definition. And if we do it in a proper way, that is in an asymptotically correct way, that is, then the accuracy drop is something that we can still live with because it's kind of negligible. So that's as far as this classification is concerned. And so there has to be a certain starting point for us to accomplish this dimensional reduction. The starting point is always the 3D model. And at the 3D model, again, you can think of in the classical mechanics approach, either the Newtonian mechanics approach or the Lagrangian or Hamiltonian kind of approach. Let's first see it from the Newtonian mechanics approach, and then see how that is essentially translated into a variational principle as we go forward. So once again, it's the four variables that are involved, that is the load, the stress, the strain, and the deformation. And unfortunately, many people in the literature use deformation almost in as synonyms for strain, whereas strain actually is obtained from the deformation gradient, not from the deformation directly. It's the gradients of the deformation which result in the strain. Of course, the deformation gradient tensor itself can be used as an example of a strain tensor, but many other manipulations, tensorial manipulations of the deformation gradient can also be used as strains. We will see examples of that as we go forward. And I mentioned in the one of the previous classes, or two of the previous classes as well, that once you choose the kind of strain, the appropriate kind of stress has to be chosen as well, as a usually as a power conjugate. That is a more rigorous way of doing it, but for static problems it could be equivalent to a work conjugate that we are talking about as far as the stress and the strain pair is concerned, the definitions for the stress and the strain. So we will use the word deformation to essentially mean a generalized sense the displacements and rotations. So all kinds of three-dimensional or two-dimensional or one-dimensional displacements that are taking place, including the rigid body-like displacements, rigid body-like rotations, the local rotations, and the warping that are that is going to happen as a 3D field. All of that we call as the deformation over there, and that's what leads to the strain, and the strain leads to the stress, and the stress leads to the load handling. So, or you can think of it in the other way, depending upon the perspective from which we are looking at it, which is the cause and the effect is kind of hazy, like in the chicken and egg story, which came first, or a seed and a plant which came first. So you can always argue out, and the winner of the argument is always the one who can argue better. It's the better debater who wins rather than the better logic or the truth that wins, because either case you are just the starting point that you define has to be different based upon the standpoint from which the observer is. So essentially it's an observer dependent problem as to which is the cause and which is the effect over here. The 3D load can be of two types. One is essentially on the body, it's the surface load loads, and very often it's not the entire surface, outer surface, that is loaded. Parts of it are loaded, and parts of it you can specify the displacement boundary conditions. So force boundary conditions and displacement boundary conditions, what are also known as natural boundary conditions, and the geometric boundary conditions, or Neumann and Dirichlet boundary conditions, etc. Various names for the same thing. So here we are talking of such natural boundary conditions as the tractions Tj, which are specified on a part of the boundary of the three-dimensional structure that we are dealing with, which can eventually also be modeled as either a beam or as a shell as well. But to start with, the derivation is from the three-dimensional model, wherein these tractions are known on the surface of the or a part of the surface of the body. And then, of course, there are certain body force distributions. We've already neglected the body moment distributions to take advantage of a symmetric stress tensor, rather than in general you could have a 9-component stress, all of which are independent if the body moment distributions are there. And since there are no practical situations for most of our applications where that is the case, we can live with that assumption, and therefore we deal only with body forces. And these are as being body forces distributed within the body rather than on the surface like the tractions. These are defined per unit volume, whereas the tractions would typically be defined per unit area. This would be defined more in terms of a per unit volume. The tractions, of course, can be sometimes idealized as discrete tractions, which are so-called concentrated forces, but essentially those are also distributed forces over a smaller region, which we are calling as concentrated forces for practical simplicity. So essentially these are distributed forces. One is per unit area, those are the tractions, and those which are distributed through the internal volume of the structure, which is called as the body force per unit volume. And we'll use the symbol big B subscript J for that. And we will also be using the big B for unit vectors associated with the deformed configuration, but that will be in bold font in the textbook or in any written material like your manuscript, etc., or your presentations. But when we use B without a bold, or while writing handwritten thing, we are writing without an underline for that, then it's not a vector. And we are dealing with something that is the measure numbers of the body forces per unit volume. The body force by itself being a force is a vector, but what we are talking of are the components over here. So let's not get confused between this notation. So, but more often than not, this is already incorporated into the inputs as we shall see later on, and therefore we will not be actually dealing with these explicitly. But remember that we are using the same symbol for both. Let's not get confused between them. Then we are using Latin indices over here, and these Latin indices, which means any one of the alphabet letters from Latin, and which is therefore in English as well, all the way from A to Z, but more commonly I, J, K, L, M, N, etc., which we use, are typically those which go on in a range from 1 to 3 unless specified. So J can take on the value 1, it can take on the value 2, it can take on the value 3 as well. So that's essentially what we mean by a dummy index over here, which is essentially a floating index. But if it is specified in a particular direction, then it's no longer a floating or a dummy index. It becomes a specific index that is associated with that particular direction. So, for example, it's the traction case. The traction will be specified in specific directions on a specific region of the boundary, and therefore the value of J would then be specific, like it could be a T2 or a T3, etc. So, next is the stresses, and once again, all of them we use the adjective 3D to refer to the fact that these are functions in general of x1, x2 and x3 if you're using, let's say, a coordinate system with the coordinates x1, x2 and x3, which in general can be a curvilinear coordinate system, but more often than not we'll be using a dextral triad, an orthogonal system, orthonormal system involving unit vectors which are perpendicular to each other, but the generic derivations are all valid for curvilinear coordinate systems as well. And remember that the cylindrical coordinate system or spherical coordinate system that you're familiar with are still orthonormal systems, because they are also orthogonal, and the unit vectors associated with those directions like ER, E theta, E phi in the case of the unit vectors of the spherical coordinate system, they are still all unit vectors and they are all perpendicular to each other. So whether it is Cartesian, cylindrical or spherical, they are all under the orthonormal system. I'm talking of an even more complicated system where each one of these are no longer straight lines but can be curves. That's what we mean by a curvilinear coordinate system, and the unit vectors associated with those directions need not be unit vectors any longer. So their magnitudes need not be one. They could be any set of basis vectors. So basis vector is a term which is a generalized notion of the so-called unit vectors that you are used to. Unit vector is an example of such basis vectors. So in general, they need not be unit vectors and they need not be along straight lines. They could be along curves, which is what we refer to as a curvilinear coordinate system. So we would see when we get into the kinematics that we are deriving everything for a curvilinear coordinate system, but essentially applying it for a specific orthonormal system because in many situations that is possible. But in many situations it may not be possible. For example, in a tapered wing where you have a wing sweep also, and therefore you might have loads which are determined aerodynamically on cross sections which are not necessarily perpendicular to the reference curve, and therefore you might need to deal with oblique coordinate systems as well. So in which case the angles between the systems between the unit vectors may not be 90 degrees to each other or mutually perpendicular, mutually orthogonal to each other. So all such possibilities are there. But here, unless otherwise specified, here I'm talking of the orthonormal system so that you're familiar with what you already do. But always remember that for complex problems, sometimes curvilinear coordinates can be useful, and our approach is always open to using the curvilinear coordinate systems as well. So sigma ij are the stresses. So once again, they are 3D, which means they are functions of x1, x2, x3 as far as spatial dimensions are concerned, but also time in the case of a dynamics problem, which is also the case with the tractions and the body forces as well. Then the strains, we will use different symbols to refer to 3D strains. We use the uppercase gamma over here, uppercase gamma as opposed to a lowercase gamma, which is looking like this. So which we use typically for the one-dimensional strains associated with beams, and we will also use epsilons and rho or kappa, which are associated with the two-dimensional strains. So here we will use gamma and kappa with the one-dimensional strains, and epsilons and rhos with the two-dimensional strains. That's to distinguish from them. We don't use that same epsilon or gamma over here. We call 3D strains as big gamma. But essentially their nature is all very similar, that they are obtained from some kind of a gradient of the deformation. So you have a deformation in the form of some displacements or rotations. You're seeing how that displacement or rotation is changing in a spatial sense, and that's how you obtain strains. How it changes in a temporal sense is what we call as velocities and angular velocities. Whether they're changing with respect to space or time like strains, or with respect to time like velocities and angular velocities, they're all behaving in a very, very similar fashion, and that is another unification in the spatio-temporal sense that we are bringing into the whole system. So if you understand statics very well, extending it to a dynamics problem is not very difficult. But here, in general, we are talking of everything varying with respect to time. So it can be a time-dependent dynamic problem, impact or fatigue or any other kind of complication that you would like to have. Finally, it is the deformation, U1, U2, and U3. So M, like any other Latin index, can take on any one of those three values, and that's essentially what we call as the deformation. So these are the four sets of variables. Now we need to relate them. First of all, the equilibrium relations, which have to one set which will relate the Tj to sigma ij, and the other set which will relate the Bj to sigma ij. The one which relates Bj to sigma ij are the internal equilibrium, whereas that which relates Tj to sigma ij are the surface level equilibrium at those surfaces where the loads are specified in certain directions. So the internal equilibrium equations, which are bringing in the body forces into picture, are these. So you can very clearly see that there is a derivative with respect to I that is involved over here, which is a spatial derivative, and there's also a double dot that is involved over here, which is a temporal derivative, and therefore there are multiple independent variables in this problem, x1, x2, and x3 apart from time. So the four independent variables, and when you have more than one independent variable, what you're dealing with is not an ordinary differential equation but a partial differential equation. These so-called Cauchy equilibrium equations refer to the mathematician and mechanician Cauchy, is essentially an equilibrium equation, and all of you are very familiar with how to derive it by taking a cuboidal element and specifying the forces or the stresses coming on each one of those phases multiplied by those infinitesimal areas to get the infinitesimal forces, and then getting to a equilibrium of those infinitesimal forces along with the body forces and the D'Alembert's force, which is essentially what you see on the right hand side, which is the mass density rho multiplied by the acceleration that is involved of each material point or particle that the particles that the entire beam or shell is composed of. So right now this is applicable to any 3D body, even a brick, which may not be considered to be either a beam or a shell, but it's also applicable to shell-like and beam-like structures, because everything in reality is a three-dimensional structure. So you're talking of sigma ij and Bj relationship over here, but it's also bringing in the dynamic aspect, and therefore the accelerations are coming into picture through the D'Alembert's force on the right hand side. The other thing, equilibrium, of course, is at the boundary or parts of the boundary where the natural boundary conditions are specified, where we are saying that applied force per unit area has to be balanced by the internal stresses. So Tj is a per unit area as opposed to body forces, which are per unit volume. So this entire equation you can see is nothing but a force per unit volume kind of a relationship. You know that Newton's second law says that the force is given by mass into acceleration, but here we are dealing with a mass per unit volume, which is what is rho, the density, and therefore it's talking about a force per unit volume. Similarly, Bj, we already said is per unit volume, and stress, you know, is per unit area. But once we take a derivative with respect to another spatial coordinate, that also becomes per unit volume kind of a quantity that we are dealing with in terms of dimensionality. It's all Newton per meter cube in the first equation, and in the second equation all the terms are having the unit Newton per meter squared, which is distributed over the area. Yes, somebody had a question? Yes, Nilesh? Nilesh, you had a question?
Hello?
Yes, Nilesh, I can hear you. Nilesh, you have a question? Okay. This is an issue. So let's see. So this is essentially the 3D equilibrium equations, which are relating the stresses to the loads, either the internal loads due to a field, environmental field in which it is. So in that sense, Bj, even though it's an internal force, it's also coming because of an external field. It could be a gravitational field due to an external planet or a star, or it could be an electromagnetic field, etc. Whatever field that this body is in, and essentially the forces that it is facing due to being in that field, it would not face those forces if it were not in any such field. That's essentially what we are talking about. So whether it is that traction Tj or the body force per unit volume, it's an influence of the environment on the body, and therefore it's coming from an external source. So next is the constitutive law, which relates the sigma to the gamma, that is the 3D stresses to the 3D strains. And we already said that it's a Cauchy material, that is sigma depends only on gamma. We said it's a Hookean material, which means that sigma is linear with respect to gamma. If it is nonlinear, we can change this particular expression to reflect that on the right hand side, your Eij KL are no longer constants. Eij KL are functions of gamma KL, and therefore as the strain increases, Eij KL can change their values. So in that sense, a non-Hookean material can also be incorporated in the same parlance. Then finally, we also said it's a green elastic material, in the sense that this strain energy density exists. So what is that? Because so far we have been talking only of the Newtonian kind of an approach, not a Hamiltonian or Lagrangian kind of an approach. So that's the place where we bring in the existence of the strain energy density, where we are saying that we multiply this right hand side along with gamma ij as well, and therefore the whole thing gets summed over gamma ij as well, and then you bring in a factor of half, and then you're multiplying the stress with the strain and putting the factor of half for a gradually loaded system, where we are therefore defining the so-called strain energy density, in terms of which everything else can be derived. So that would be the starting point. We will revisit that in a more detailed sense once we start applying the variational asymptotic method. But essentially, this is the connect between the Newtonian mechanics on the one hand and the Hamiltonian mechanics on the other hand, where that strain energy, and along with the work done, along with the kinetic energy, etc., all of which we will derive an expression for, will all go into defining the so-called Lagrangian or Hamiltonian, and then apply a particular stationary principle to derive the governing equations of motion. So final set of equations are the kinematics. Once again, three-dimensional kinematics, because they're dealing with 3D deformation and 3D strain. And in a geometrically linear model, you would have only these two terms. So whether it is a normal strain or a shear strain, or both are included in the same definition, just that your K and L will take on the same value, either 1,1 or 2,2 or 3,3, in order to get to that particular result. Whereas in the case of shear strain, K and L will not be equal to each other. It could be 1, 2, 2, 1, 3, 2, 2, 3, or 3, 1, 1, 3. So those are the 6 shear strains that you could have. So the same definition holds for either one of them. And the first two terms are all that is necessary in the case of linear kinematics, or what we call as a geometrically linear problem. But we will be dealing almost always with a geometrically non-linear problem. This is essential because we are dealing with thin shells and or beams which are slender. That is, the cross-sectional dimensions are very small compared to the length. Once we have stubby beams or thick shells, then this third term doesn't play a very critical role most of the time. instead the transverse shear strain starts playing a more critical role. So it's not very close to a plane stress kind of an approximation. In any case, even for thin shells, we do not make the plane stress approximation, but let the mathematics come up with a plane stress solution as the zeroth order approximation by itself, rather than ignoring the sigma I3. So sigma I3 should be shown to be small compared to sigma alpha beta, not assumed to be zero to start with. So that's essentially what that is. The second, term or third term that we see here is essentially a quadratic term. Again, this is for a particular type of the strain displacement relationship definition. Once we get into the kinematics derivation, we will look at other definitions of the strain displacement as well. This is one common definition that I'm sure you would have all been exposed to in your undergrad as well. Then that's as far as the internal strain displacement relationship is concerned. Just like here we talked of internal equilibrium and we talked of an external equilibrium at the boundaries or the surface, and similarly kinematics also we talk of certain boundary conditions which are specified on the boundary, which could be in terms of displacements or it could be in terms of rotations. So and at certain locations it could be both which are specified. For example, in the fixed end of a cantilever beam, we are specifying both the displacement as well as the rotation to be zero. So that's an example of both being geometric boundary conditions. Whereas in the case of a simply supported beam at a hinge, you see that the moment equal to zero is a specification of a natural boundary condition like Ti that we were talking about. Whereas the fact that the displacement is zero is a geometric boundary condition. So a hinge is an example of a mixed boundary condition of one natural and one geometric, whereas a fixed end is an example of both being geometric. A free end is an example of both being natural boundary conditions. So, and in reality, we don't have these idealized kind of situations. So we could have a certain displacements, certain rotations, or certain forces and moments being specified at different locations. So such combinations are there, which may not be an idealized hinge or idealized fixed end or an idealized free end. So in such situations also we should be able to solve the problem. So we are talking of a very, very generic set of naturals over here, right? So with that, now we will go into some specific examples, and then we will put all of these examples, stitch them all together. Still remember, I'm striking out AE 352 to refer to the fact that we are dealing with the conventional approach to dimensional reduction. But I will use the variables that we are going to use as well, so that you can see the parallel in terms of which variables are being used there, and but the approach is going to be slightly different, the way we do it without the ad hoc assumptions that are involved. So the problem involves here a cantilever, but any other boundary condition might be equally good as well, and we are talking of a one-dimensional element. So you see that the cross-sectional dimensions in this cross section that you see over here, along x2 and x3 directions, which I can define along these two. This is x2 and this is x3, so that you get a dextral triad over here in an orthonormal system, and x1 is already shown over here along the length that you see over here, and this is the cross section that we are visualizing over here. It could be any arbitrary shape, thin walled or thick walled or solid. It could be a hollow closed section, or it could be an open section, whatever it could be. But the load that you're applying over here is tip load of axial tension P, which in the case of a column would become reverse in direction, and therefore it would be a compressive load. And x1 varies from 0 at the fixed end to L at the free end. And the actual examples in the aerospace applications are rotor blade flex beams, Flex beam is a term, it's a single word which is very commonly used in the helicopter industry to refer to the skeletal structure of a rotor blade, whether it is the main rotor or the tail rotor. This is what offers the strength and stiffness to the overall structure. On top of that, you have an airfoil section which creates the aerodynamic shape that is required for the rotor blade, but the internal load bearing structure is predominantly this particular flex beam. So that's a classic case in the case of especially hingeless and bearingless rotors. That is a cantilever kind of a condition, whereas in a fully articulated rotor system, you would have the blades which are having hinges and or bearings, and therefore you need to specify the appropriate boundary conditions at the end where the blade is attached to the hub. But in the case of most composite beams, flex beams, we are moving more towards hingeless and or bearingless situations, and therefore cantilever boundary condition or a fixed boundary condition at the hub is a reasonably good approximation for most practical purposes to start with. So then the other examples are in the fixed wing in the case of spars and stringers, both in the wings as well as in the stabilizers, horizontal, vertical, as well as the fuselage. So all of those are situations where the cross-sectional dimensions are small compared to the length. So for this kind of a member, once again we put it into the same set of analysis paradigm that we go to, or a design paradigm as well, which is that there are four quantities which describe the mechanical state of the structure, unlike in the previous slide where we talked of all of them as three-dimensional quantities depending on x1, x2 as well as x3. Here they all depend only on x1, and what those quantities are the 1D load, the 1D stress, the 1D strain, and the 1D deformation. So just as a conceptual thing in terms of introducing them and distinguishing them from the so-called 3D stresses, strains, loads, and deformation that we saw in the previous slide. That is the purpose that this is serving, as well as building block towards the overall beam constitutive law. So the load that you can see over here is something that is applied only at the free end where x1 equal to L, and therefore this hat should actually be on the top. So it should actually be F1 hat over here. So all these hatted quantities are discrete boundary conditions, and the fact that I'm using the subscript 1 is to show that it is along the x1 direction, and it's at a particular location. That's why we are calling it a hatted quantity, and that particular location here happens to be x1 equal to L. It's dependent only on one spatial coordinate, which is x1, and that spatial coordinate is also fixed at a given value of x1, that is L, and there you're specifying the load P, and therefore F1 hat at L is equal to P. That's essentially a natural boundary condition, but that also happens to be the load specification. So the load is specified in terms of that boundary condition, that P, that is over there at that particular location. The stress itself, instead of dealing with actual stress sigma 1, 1, we are going to deal with the stress resultant, which we call as F1. So in all of beam problems, we will give up that 3D stress sigma and instead talk of a 1D stress resultant, which we will call as F1, which will have the units of Newton, but still we'll be calling it as a 1D stress. So that's essentially what it is, but it's how it is obtained, how it is defined. So this could actually be a definition. So I can put a triangle on top of the equal to sign to refer to the fact that it's a definition. That F1 of x1, this is varying along x1. So it's a one-dimensional variable. It doesn't vary along x2 and x3 because that three-dimensional stress, which was actually varying about all three, that is x1, x2, and x3 apart from time in the case of a dynamics problem. Here we are talking of so here we are talking of three spatial directions. But you see those angular brackets. Those angular brackets are defined over here. That any quantity, if you put between angular brackets, which I am representing by any arbitrary quantity as a dot. So what you're doing is you're integrating that quantity over the cross-sectional area. So A being the cross-sectional area that you saw already over here, that is your A, and the same A is over which you're integrating it. If you have an orthonormal system, which is what we will have for most part, it's all that there is. But if you have a curvilinear coordinate system that I described to you just a few minutes back, then you cannot just integrate over the area. We have to bring in what is known as a metric determinant g and its square root. So square root of g. What this g is, hold on with me for a while. All that you're doing in that case is, in the case of a curvilinear coordinate system, it would be in terms of the basis vectors. So suppose I call the basis vectors as, let's say, gi. Then I'm dotting gi with gj, that is basically the inner product of these two vectors, and I get a matrix which I call as gij, elements of which I call as gij. So it's a 3 by 3 matrix corresponding to I and j taking all the values 1, 2 and 3. And once I get that matrix, I then take the determinant of that gij matrix, that 3 by 3 matrix, and that determinant of this is what I call as g over here. Okay, so that's essentially what this g is, but here I'm taking the square root of g. And it's very easy to see that if gi and gj, these basis vectors, are the unit normal vectors in an orthogonal system like e1, e2, e3 along your x1, x2, x3, and they're all perpendicular to each other and they're all having a magnitude 1, then you can see that ei dot ej would, in an orthonormal system, ei dot ej, very easy to see, is nothing but the Kronecker delta delta ij, right? So which will take on the value 1 if I equal to j, and it will take on the value 0 if I not equal to j, right? Which means that the matrix that you get by putting this delta ij into 3 by 3 matrix, that matrix would be nothing but the 3 by 3 identity matrix, and the determinant of an identity matrix is 1. So your g will be 1 and square root of g will be 1. So this angular bracket definition would just become an integral over the area of that quantity which is within the angular bracket. So it's just an integration over the cross-sectional area. So right now you can just think of it as an integration over the cross-sectional area, but for the definition to be general for a curvilinear coordinate system as well, where you might be dealing with unit vectors which are not unit vectors but are general basis vectors like the g's, and which might be along curvilinear tangential to curvilinear coordinates rather than to orthogonal set of coordinate systems. So x1 and x2 and x3 are not varying along perpendicular directions but along some directions which are not, of course, collinear or coplanar. In other words, they are linearly independent vectors, the G system as well, just like the E system, but the fact that they are not necessarily making 90 degrees with respect to each other means that your dA element will no longer be just your dx2 into dx3. Here in this case, the cross-sectional area is along x2, x3 with the orthonormal system, x2 over here and x3 over here, and therefore any element that I have over here can be thought of as dx2 along the x2 direction and dx3 along the x3 direction, so that your dA can be thought of as a product of these two, that is dx3 into dx2 will be equal to your dA. That is not the case in a curvilinear coordinate system, as you can very easily see. Just draw two curves and then you would see that if it is dx2 along this and dx3 along this, and I multiply dx2 and dx3, I will not get that area that it encloses. So that's why the need for bringing in this square root of g. So we will see some examples where this will become a little more clearer. But for now, all that suffices is to see that the angular bracket essentially means an integration over the area, and in this case the integration over the cross-sectional area, and therefore because sigma 1 1 is along the on an area which is having a normal about the x1 direction, that is the b1 unit vector, and therefore it's acting in the one direction, so therefore it's a normal stress which is acting on the cross section, which is essentially the stress that would be created by an axial load like this, whether it is tension in a bar or a compression in a column, and therefore that integration over the cross-sectional area is essentially going to give at any given cross-section what is the tensile force or a compressive force that is acting, which is essentially nothing but is not a external force, but it's the internal reaction to that external force P that you're applying. P at the end x1 equal to L is the only load that you're applying in this example problem. In a general problem, of course, it could be a distributed axial load, as in the case of a helicopter rotor blade, where it is the centrifugal force that is coming. So at any given cross section, if I cut the helicopter rotor blade in an imaginary sense, the axial load that would be coming is because of the rest of the blade from the tip, which is the free end, to that particular location where I want to determine the axial load, and therefore the centrifugal force because of all of this mass up to that point is what I will get. At some other location inboard, it will be even larger centrifugal force, etc., until it maxes out at the location where the blade is attached to the hub. So you could see that therefore it's a distributed axial load that you are having. Even in the case of a civil engineering column structure used to construct buildings, you can see that as you go further and further down towards the ground, you are having larger load, because it's the weight of not only whatever is sitting on the column, but the column self weight as well, which keeps increasing until you reach the bottommost point where it is attached either to the next below floor or to the ground. So you see in all these cases you have either distributed tensile or distributed axial loads, but in the example that we are considering over here, it is a tip load which is a concentrated load, and it is tensile in nature that we are showing over there. And so essentially when you are integrating the stress over there, you are getting back that quantity, which is nothing but a reaction at that location. So notice that two different symbols that we are using. One is the F1 hat, which is equal to P at x1 equal to L, and the F1 without the hat that you are showing over here, which is a general function of x1, and it is essentially a reaction of the structural material to the load that is applied, and that is equal to an integration of sigma 1 1. And this would always be the case whether you have the concentrated load like in this example problem, or a distributed load like in the real problem, because when you are integrating in an internal region, you are taking advantage of the so-called Saint-Venant's principle. It's only close to the boundary. How close? By a certain order of the cross section. So if the cross sectional dimension is of order d, let us say small d, then a few elements of d, let's say 2d or 3d, up to that, the way in which the load is applied will matter. For example, whether it's a concentrated load like what I have applied P, or I break P into two parts, P1 and P2, not necessarily equal to each other, but P1 is applied at the top end and P2 is applied at the bottom end. But if P1 plus P2 is equal to P, once again at this particular location I'm still going to get the same load in the axial direction. Of course there can be a moment, etc., that is happening in addition to the axial load, depending upon the relative values of P1 and P2 and the relative locations at which they are applied, etc. But if the resultant is the same, two sets of loads distributions can have the same effect in the internal regions, which is what this takes advantage of, that you are just integrating sigma 1 over that cross section's area rather, to get to what you call as the stress resultant. So whereas the stress is a three-dimensional stress, it's a function of all three spatial coordinates, your F1 is a function only of x1, and therefore it's a one-dimensional variable F1 of x1 that we are dealing with over here. So similarly, when we come to the strains, we have a strain gamma 11, which is a three-dimensional strain which depends on x1, x2, x3. Now we are mapping that to a one-dimensional strain, which is a function only of x1, and we are using a smaller gamma to refer to that, as opposed to the uppercase gamma that we use to refer to the 3D strain. So this gamma 11 is a function only of x1. Coming to the deformation, you would have in general three-dimensional deformations, for which you could use some other symbol, but we are using the symbol small u to refer to one-dimensional deformations, which once again are therefore functions only of x1, which is the dominant dimension, because the length is large compared to the width and the thickness of the beam. So u1 of x1 is what is the deformation specified all the way from x1 equal to 0 to L, and in this case that's an unknown quantity which is to be determined rather than specified. What is specified is only at the fixed end, where fixed end you see that x1 equal to 0 is the fixed end, and at that location, because it is fixed, you would have the axial displacement equal to 0 as well. So once again, this hat should be over the u1. Sorry for the misprint over there. So it should actually look like this, u1 hat. Okay, so u1 at x1 equal to 0 is equal to 0, which is essentially a geometric boundary condition, as opposed to this, which was a natural boundary condition. So this is an example of a natural boundary condition. This is an example of a geometric boundary condition. Okay, so next we bring in the connection between these, that is the equilibrium equation, the constitutive law, and the kinematics. Here is where the distinction comes. That's why I've striked out A350 to showcase that this is not the way we are going to handle it, but essentially the meanings of the variables will remain the same, but the actual equations and the way we approach the problem more through a variational approach, etc., is going to be different. Here it's only to see the connection that is happening from the models that simpler models that you're already familiar with, to see that it's the same set of variables that we are playing around with, but we are playing around with it in a more complicated way, in a more rigorous way, academically acceptable way, so that we can get more accurate results. That's all that we are doing. So it's just like you're used to playing certain games on your smartphone, where you have challenge levels, and the initial level would be a beginner's level, where rules are very, very simple. As you become an expert at that level, you go on to the higher levels and the rules become more and more stringent, the game becomes a little more complicated. That's all that, but you're essentially playing around with the same set of entities, because it's the same game that you're playing. So that's essentially these variables, law of load, stress resultant, strain 1D strain, and the 1D deformation that you're all dealing with, but you're going to be dealing with in a more rigorous and more accurate fashion. So along with the equilibrium equation, of course, you have the natural boundary conditions. In this case, it's a free end, x1 equal to L, which means that at that free end, you're specifying there are no other loads. That's why it's free. But there is one particular load, that non-zero load that you are applying, which is your P, which is an axial load. So that's essentially the natural boundary condition at x1 equal to L. And also we are saying that on this surface, even though this might be in air, which means that there is actually, remember, atmospheric pressure that is acting. Any beam model, we tend to ignore that. There's actually a normal stress both sigma 2 as well as sigma 3 in those directions which are acting, which is equal to the atmospheric pressure that is there, which is essentially causing a compression. Of course, in this kind of a situation, you may not have a resultant force that is there, but still that is creating a certain compression all around, which will cause a certain extension in this particular direction due to the Poisson's effect. All of that is kind of ignored in these kinds of models. But what we are saying is that sigma 2 and sigma 3 are 0, so that we can have a simpler constitutive law directly between sigma 1 and big gamma 1 through the Young's modulus E. Otherwise, we have to bring in the Poisson's ratio and sigma 2 and sigma 3 as well. But you can see very clearly that the boundary condition in a realistic beam is where sigma 2 and sigma 3 are non-zero values. So now in the simple example that we are taking, sigma 2 and sigma 3 are assumed to be 0, and that's as far as all the natural boundary conditions are done with. Now we go to the geometric boundary conditions, which pair along with the kinematics, and that geometric boundary conditions there is that it's a fixed end at x1 equal to L, and we have already specified because of that what is the value of the displacement at x1 equal to 0. It is equal to 0 because it's a fixed end. Next thing is an assumption about the constitutive law, which also we cannot make because we are dealing with in the course composites. But in this simple example, we take this beam to be made, or bar to be made out of metal. So let's say the constitutive law is isotropic, so which means that is for an isotropic material, which means that we don't need indices or subscripts for the Young's moduli, Poisson's ratios, etc. We can just use one Young's moduli, and which is E in this particular example. So what are these equations? So the equilibrium equation is that the P has to be balanced with F1 at all locations because there's no other distributed axial load coming. There's only a tip load that is there. So P is equal to F1 of X1, and which in turn becomes just sigma 11 by sigma 11 into A if sigma 11 is uniform, which will be the case because of Saint Venant's principle in the interiors, whereas it will not at the location where the load is applied, as well as for small region close to the end, wherein you cannot use a dimensionally reduced model. So this is a very important takeaway from this, that the dimensionally reduced models, whether you are doing it in the conventional approach or using VAM, etc., will not give you accurate results very close to the boundaries, because there the actual boundary conditions will come into picture, and those are typically three-dimensional boundary conditions, and therefore three-dimensional model is what will work in those locations close to where the boundary conditions are specified, whether it's the load or whether it's the displacement, even at the fixed end there for that matter. So in other locations, sigma 11 is a constant at any given x1 value. It's not varying with respect to x2 and x3, so that integration, already square root of g became 1. This became 1 because we are using an orthonormal system. Then this dA is dx2 into dx3, and sigma 11, that is this dot that you're seeing here, came out of that integral and just became an integration of dA, which is nothing but A, which is the area that we have pointed out over here. So this becomes sigma 11 into A. It's a very, very simple problem, but I'm spending so much time here, even though I've also spent some time using a different slide in the flight vehicle structures course, because this helps you understand all the variables in such a clear and crisp way that once you go for more complex problems, a very general problem, you would have absolutely no issues in handling all of these variables and equations. So that's the so if it's very important that you spend a little more time revising through this, so that you understand the meanings of all these variables. The difference between sigma 11 and f1, for example, both are called as stresses. Sigma 11 is a 3D stress and f1 is called a 1D stress, but actually it's a stress resultant because we are integrating over the cross section cross-sectional area. Similarly, if it is F2 or F3, we will be integrating sigma 1, 2 or sigma 1, 3 respectively over the cross-sectional area. If it is an M1, we would see what we will do in the next slide. Similarly, if it's an M2 or M3, which is a bending moment, how we will integrate. But essentially, whether it is any one of the FIs or MIs, we are calling them as 1D stresses, or actually 1D stress resultants. And they are what are replacing those sigma ij's that we had in the previous slide, where we listed out all the 3D quantities. So same thing holds as far as the strains are concerned. The distinction has to be understood between the big gamma and the small gamma. Yes, in this particular example, both happen to be the same. Your big gamma 11 is equal to small gamma 11. But when you have in the same problem not only an axial load but bending also coming up, you know that bending is also going to cause a gamma 11 in terms of the big gamma 11. That is the this gamma 11, that is the 3D strain, can be caused both by a tensile load as well as a bending load. A bending load causes bending stresses, which you know are nothing but axial stresses, tensile and compressive on either side of the neutral axis, and they are going to add or subtract to the tensile or compressive load that you're going to apply over here. So essentially, in terms of the strain also, the big gamma 11 is going to have contribution not only from the small gamma 11 but also the bending curvatures kappa 2 and kappa 3, which are the curvatures along these two directions that the bending can happen in general. So you are having something, this big gamma 11 is not only a small gamma 11, but it will have terms like x2 times kappa 3, x3 times kappa 2, etc. with the appropriate signs, which are adding up algebraically to this gamma 11 to create the overall big gamma 11. So in this problem, you don't see that distinction because there's only an axial load and this is an isotropic material. There are no couplings, and therefore and you're also setting sigma 2,2 and sigma 3,3. So the only possible coupling was the Poisson's ratio coupling. That is also gone now. So everything is direct relationship at the diagonal level, and what you're having is big gamma 11 is same as small gamma 11. But in reality, when we have a general 1D structure, you will not have only small gamma 11, you will have other terms as well. So that's as far as the equilibrium equation is concerned, that P is equal to F1 of x1, which in turn is equal to, in the interior, sigma 11 into A in terms of the 3D variable that we are dealing with. Then the constitutive law is a 3D material constitutive law, which depends purely on the material, and that material constant that is coming is your Young's modulus E, only one value because it's isotropic material. So sigma 11 by E is equal to gamma 11. Even for an isotropic material, the left hand side would have had terms like sigma 22 into mu by E and sigma 33 into mu by E, subtracting out on the left hand side to give the total gamma 11. But because we have already said that the other natural boundary conditions are that there is no sigma 22 and sigma 33 acting anywhere in the beam, so therefore you are having those two vanishing as well, and therefore only this simple expression that you're familiar with as Hooke's law is what you have. And similarly, in terms of the geometrically linear strain definition over here, you just have u1 comma 1. Otherwise you would have had at least a quadratic term which is adding on to this, which is coming up. But here we are ignoring geometric non-linearity as well for this simple example, only to introduce the variables and to see where all of these fits into the bigger picture. So gamma 11 is equal to u1 comma 1, which many a times we will derivatives with respect to x1 we will write it as just a prime. So this is a notation that we will use, just like dots are used to refer to time derivatives, the primes are used to refer to the spatial derivatives along the larger dimension, in the case of the beam, the x1. So then we go on to combining these. Let me avoid the clutter. Okay, so you would see that you can substitute. So for now we will not bother with this kinematics, we'll leave it aside. We will not get it in terms of u1. so that this is something which is valid even for geometrically nonlinear problems. So all that we do is we substitute this constitutive law into the equilibrium equation over here, so that we can eliminate sigma between them, which is a 3D stress, and get a direct relationship between the 1D stress resultant, which is your F1, and the 1D strain, which in this case is gamma 11. And it's very easy to see that you're getting an A from here and an E from here, and therefore you're getting an EA as the multiplying factor over there. So in a geometrically nonlinear problem, what will happen is very easy to see. As I pull this, there is a Poisson effect even in isotropic material, so the area will decrease. So as the area decreases, you are going to have the EA which is changing. So in other words, this stiffness or axial stiffness that you have is going to change even in this simple problem that you're going to have. And of course your gamma 11 definition will involve not only U11 but also the nonlinear terms over there. Now the more important point is to see that because we have gone from a 3D model to a 1D model, this purity is lost. We used to say that the equilibrium depends only on the natural conservation laws, the constitutive law depends only on the material, and the kinematics depends only on the geometry, but no longer so. There is a mix that has happened in this 1D constitutive law. So this is an example of a 1D constitutive law, as opposed to this one, this particular equation, which is a 3D constitutive law. So you see that the 3D constitutive law depended purely on the material. The 3D equilibrium equations depend purely on the conservation laws. The 3D kinematics depends purely on the geometry. But once we have gone to a dimensionally reduced model, in this case a 1D, but even in the case of a shell, it's a 2D. Once we do that dimensional reduction, things are going to flow in, because we have reduced the cross section, which was a finite area A, into a point of area 0, and lumped all of its behaviors, all of its properties, characteristics to that point on the cross section, and the loci of all those points becomes your reference curve. So that's essentially what you're doing here. So yes, it's still based on conservation law, material and geometry, but not in the pure sense. So let me clear those pen markings. So let's see where all of those dependencies have gone. So E is there, that is coming from the material. A is there, that is coming from the geometry, and this equal to sign that is there is coming from the conservation law. So all three have gotten together into this single system that we are talking about here from the 3D level. But from the 1D level, there are certain equilibrium equations that are going to come, and the 1D kinematics that we have not yet touched upon over here, and with the geometric nonlinearity falling into place as well. So all of that will come. And further, when we deal with curvilinear coordinate systems, we'll have to deal with the square root of g, which is not equal to unity. So this is as far as this particular example is concerned. We'll go through two other examples very quickly and then combine them in the next class. So those of you who are willing to wait and ask me any questions, I'd be most happy to answer.
Hello, sir. This side Shravan here.
Yes, please, Shravan.
Sir, how small dimension of cross section should be in order to call that structure a beam? I mean, is there any specific value to that?
Okay. So see, this is a loaded question, because it all depends upon what you're trying to do with that model eventually. What are the quantities of interest that you have, which are typically the 3D stress field, the 3D strain field, the 3D displacement field. If that's what you're interested in, for all practical purposes, and it's a statics problem that you're dealing with, then you can say that cross section, thumb rule, this is a thumb rule. So the cross-sectional dimension should be less than or equal to 1/10 of the overall length of the beam. So this will give you typical accuracies in the stress, strain, and the displacement, rotation fields that you eventually require to be almost on par with the 3D finite element results or 3D elasticity, because this is a very simple problem like this where even closed form analytical solution is possible using the theory of elasticity. So to agree with that, you would require that the cross-sectional dimension is of the order of 1/10 typically. What happens if it is slightly less this way, that way? Obviously your accuracy is going to get tweaked either this way or that way. So it's all a question of what kind of tolerance levels you are specifying with respect to the fields of interest that you're dealing with. Again, for example, if you're not interested in the stress at all, you're interested only in the, let's say, the displacement field, then you can use a displacement based finite element analysis and still get very good results. For example, if you are interested in the stress as well, which means you can also do failure analysis, etc., then you might be interested in getting the stresses also as accurately as the displacement, which is not possible in a displacement based finite element formulation, in which case you go for a mixed finite element formulation wherein the stress resultants like F1, etc., are included in the finite element model, and therefore you're dealing with all of them as unknowns in the problem setup, and therefore you're solving for all of them simultaneously with the same level of accuracy. Whereas with the displacement based approach, you are solving for displacement, then you have to get the strain by taking derivatives of the displacement, and because this is a numerical problem, the numerical derivative means further errors that are coming with that, and therefore once you get that strain and use it with the constitutive law to get the stress, by that time you have added further errors, and therefore the stress will be less accurate compared to the displacement field results that you get. So this kind of a question that you ask should always be accompanied with what is the end purpose of what you're doing, and based on that the answers have to be sought by you yourself. But as I said, the thumb rule for most cases is 1/10, and similarly for a shell-like model, if the thickness of the shell is about 1/10 of the smaller of the other two dimensions, for example in this case the smaller dimension would be the chord rather than the span for this plate-like structure that the wing can be modeled as, then the thickness, maximum thickness that you have anywhere should be about 1/10 of this. So then you can use a beam-like model and get very accurate results, even with a zeroth order approximation, which is the classical approximation that you would end up with, which is like a Kirchhoff-Lau kind of a theory for this, or a Euler-Bernoulli kind of a theory for a beam like this. But if you go for something that is shorter or stubbier, in other words your 1/10 becomes let's say closer to 1/8 or 1/7, 1/6, etc., then you would still get good results but not as accurate as before. And if you want as accurate as before, you might have to go for a first order approximation, which is a Timoshenko-like model for this, or a Reisner-Mindlin-like model for this, which are asymptotically correct, unlike the original Timoshenko and Reisner-Mindlin models, which are not asymptotically correct. So these things that you will get used to as you start applying it to practical problems, and you are the one who is going to dictate the levels of accuracy that you're interested in, which of the end results, and not always you're interested in all the fields. Sometimes you're interested in a particular thing and its accuracy alone matters. You can work backwards to see the sensitivity analysis and see what level of the cross-sectional dimension to length that I can take in order for the theory to be applicable. And all that I described so far in answering your question is valid only for statics. Once you go for dynamics, as I mentioned to you in a previous class, you should not be comparing any longer with the actual length, but the dominant wavelengths of deformation for the beam, or the dominant wavelengths of deformation for the shell that you are interested in. Okay, sure.
Thank you very much, sir.
Yeah,
If time permits, can I ask one more question?
Sure, go ahead. Yeah.
Sir, though it's not related to this current session which you took, but at some point of time you mentioned those things. Sir, how does bending curvature get into the axial strain for a beam-like structure?
How the bending strain gets into?
So let me repeat it again.
Yeah.
So how does bending curvature
Yeah.
get into axial strain for a beam?
Okay. Very easy to see that. In fact, we will cover that in a later class. But for example, if I have a bending moment over here, let's say, okay, we'll call this as m naught. Okay. So now if I have a bending moment like this, what actually happens is that you know that there is something called a neutral axis. Right? So that neutral axis is by definition that along which there is no extension that is happening in spite of the bending. And anything above the neutral axis for the direction in which I have applied m naught will undergo compression, which means there is, if I take an element on the top fiber over here, I would see that its length will no longer remain L, it would have become smaller than L. And similarly, the bottom fiber or anything below the neutral axis for that matter will undergo some tension, so it would have become L plus some delta L, where delta L is positive, right? So that these are the changes that are happening, which means that there is a normal strain big gamma 11 that is happening for any other location other than the neutral axis. So some are having negative gamma 11, that is the top half, and the bottom half is having positive gamma 11 because of the tension. I'm saying half in a crude sense, where it's basically need not, because the neutral axis need not be necessarily at the middle. It can, depending upon the shape of the cross section, it can be at different location. There's one part which is under tension, which is at the bottom, and another part which is under compression. So now it's very clear that this m naught is causing a gamma 11. How it is causing that depends on how far that location is from the neutral axis, and that is essentially your coordinate x3 in this particular example, and therefore the curvature that is happening over here is about the x2 direction. So this moment is also about the x2 direction, so I can call it as m2, and similarly the curvature that results out of it I can call it as kappa 2. So this kappa 2 is what is going to cause, if kappa 2 is 0, in other words m naught is 0, then you would have no location at which the bending would be causing these axial strains, either compressive or tensile. As you keep increasing m naught, your m2, that is, then kappa 2 increases, and therefore the wherever there is tension and compression, the strains will also start increasing. So now how much it increases by is essentially proportional to how far it is from that, which is your x3. So essentially what you're having is a product of x3 into kappa 2. More the kappa 2, more the strain, more the x3, more the strain. So this I'm explaining to you from a physical perspective, but a mathematically rigorous way of deriving this is what we will see in the coming classes when we deal with the WAM way of deriving the kinematics, and then the geometrically exact kinematics, that is, and then the development of the overall paradigm that we are interested in. But here it's very easy to see that at x3 equal to 0, in spite of this additional term coming over here, we have to check the signs in terms of whatever we have defined. It could be either plus or minus, and of course similarly if there is a bending in the other direction, it would have an x2 kappa 3 coming from that as well. But essentially what is happening is that one factor determines how far it's from the neutral axis, and the other determines how much of the bending curvature is there. The more the bending curvature, more the axial strain contribution. The more farther it is from the neutral axis, the more the bending strain contribution, and therefore all of these contribute towards your 3D extensional strain, not to your 1D extensional strain. The 1D extensional strain is at the neutral axis or whatever your reference axis might be. What is the extension or contraction that is happening per unit length? So that is essentially what your gamma 11 is determining. That's what you can see in this simplistic definition of geometrically linear model also is concerned. It's a U1 prime. Whereas the others depend on U2 and U3, because your kappa 2 and kappa 3 will be dependent on U3 and U2 respectively, the second derivatives of that, which is what the curvature essentially is. So does that answer your question and to how the bending curvatures contribute towards the axial strain?
Yes, I did answer.
Okay.
Thank you very much.
Welcome. So anybody else? Any questions? Yes, Nandakumar.
Sir, suppose in this problem, so if we rotate it vertically and consider the gravitational effect into in this the stress resultant will have that TJ term.
So what you're saying is that this is how the beam is.
Yes.
Okay, and you're considering the gravity and what the axial load or the bending load problem?
Both, sir. Both, sir. Axial load and gravity.
Gravity or moment is not there, right?
No moment.
No
sir.
moment.
The
Okay.
axial considered.
So let's say this is P and this end is fixed, bottom end.
Top end is fixed. Bottom end is loaded, like
Okay.
weight.
Oops. Okay, it's the self weight of this which is acting.
Yes.
Okay.
The self weight along with the end loading, sir, at the pole.
Okay.
Sir, in this case, like we have both like boundary condition at the P value at L, and also the TJ as well as PJ terms.
Yeah, correct.
If we write the stress resultant in this case, it will be like it will be a single equation considering both BJ and TJ terms. But in the 3D analysis, there was separate equations pertaining to like if you can open that slide, sir. It's a separate relation, like one equation represent TJ relation and another representing BJ relation. Like, is there any third equation which relates both of them?
No, see, essentially what is happening is that all of these are not happening independently, right? See, because even that sigma ij comma I that we have, this is valid not only for the points in the interior of this, but also the boundary points. So that equation, that whatever we have over there, the Cauchy equilibrium equation, is valid not only at the boundary points but also the interior points. Similarly, your boundary condition that is there is relating the same stress quantity to the tractions that are applied on the boundary, which in this case is P, which need not necessarily be a constant. Let's say it's applied as a distributed force over there. So then you see that over that region, it's essentially the stress balance that is happening. We are still referring to the same sigma that is over there. So in other words, these are equilibrium equations at different locations, but they're all going to get connected because it's a connected body that we are dealing with. It's the same body's boundary that you are actually dealing with. So that's the reason why everything gets into the same thing. So here you're having the self weight. Let's say this is having mass density of rho. So then rho into A gives you the mass per unit length, which is, let's say in SI units, kilogram per meter that you're having over here. So that's of any element that you take over here. It's going to be the cross-sectional area into that, and that's going to be a distributed load that is there. So if you remember in the one-dimensional equations that I summarized in the flight vehicle structures course, there are certain quantities in this particular example. Let's say this as the x1 direction. So this is becoming your f1 hat. at x1 equal to L. This is your f1 hat at x1 equal to L, just like what we considered in today's class problem, whereas this is an internal load that is coming, which is like a distributed load, and that would come in what is known as your small f1. If you remember those equations in which we had f prime plus k tilde into f, etc. So there you would have an additional term on the left hand side, which is your f1, into which this thing like a distributed load, either coming because of a body force or an actual applied force that is there, because it could also be, say, let's say you're attaching some something to some sticky stuff to this, which is having its distributed weight also coming downwards. So that is also, all of those kinds of distributed loads are going to be accommodated into this small f1 of x1. So this is a distributed load as opposed to this, which is a concentrated load. Sorry, this is a concentrated or discrete. This will alter the governing differential equation itself, whereas this will alter the boundary conditions, in particular the natural boundary conditions. So that's the way in which it comes. So the concentrated loads are affecting the boundary conditions, whereas your distributed loads are affecting the governing differential equation. But you know that the actual solution to the boundary value problem cannot be obtained only with the governing differential equation. That will be a general solution. There you would not get the effect of P. But once you apply the boundary conditions, the entire boundary value problem is solved, and therefore you would have the effect of both P as well as rho A. Clear, Nandakumar?
Yes, sir. Clear, sir.
Yeah.
Thank you.
Yeah, welcome. So I think with that we'll conclude today's class. We'll catch up on Monday. Yeah. And Monday is also the day on which your videos are due. I look forward to it.
मृत्युंजय मंत्राः
त्र्यम्बकं यजामहे सुगन्धिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् ये ते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा